When you think about AI today, it feels like it's just everywhere. It's in your phone, recognizing your face. It's in cars that are learning to drive themselves, these huge language models that can write poetry.
It's completely woven into the fabric of our lives now.
Right. But if you sort of peel back all those layers, the big tech companies, the flashy product announcements, who's the person who actually built the engine? Who is the architect of the fundamental tech that lets a machine see?
That's the question we're digging into today. And the person behind that curtain, our subject, is Yann LeCun. He's a French-American computer scientist, and his work really built the bridge between these, abstract academic ideas and AI that could actually be industrialized.
He's known for deep learning, of course, but also computer vision, mobile robotics.
He's foundational in all those areas. And you mentioned he's French-American. That dual citizenship is actually, I think, really interesting.
How so?
Well, his career is this perfect blend of that European tradition of deep theoretical work with this very American drive for massive industrial scale application. Even his name, LeCun, has this deep history. It comes from an old Breton word meaning John.
So a career that really mirrors his own identity.
Exactly. But the big claim, the place you have to start with him, is his status. He is one of the three figures who are, universally called the Godfathers of AI.
Or more specifically, the Godfathers of deep learning.
Right, a more accurate term. And that trio, that's him, Yann LeCun, alongside Yoshua Bengio and Geoffrey Hinton. And their work, it didn't just improve AI a little bit.
No, it was a complete paradigm shift.
It was a revolution. They took neural networks from this kind of marginalized, almost forgotten corner of academia in the 80s and 90s, and they turned it into the single most important technological engine of our time.
Okay, let's unpack this. So our mission for this deep dive is to trace the history of his most famous invention, the Convolutional Neural Network, the CNN, and really understand how he took that idea from a sketch in a lab notebook to something that's driving entire global industries. We've got a great stack of source material for this. It covers his whole career, from his education, his time at Bell Labs, NYU, Meta, and a list of awards that is just, well, it's pretty staggering.
And that path is so important for you, the listener, to understand if you want to get a real handle on AI's history and where it's going. His career is like a perfect roadmap for how a technology matures.
What do you mean by that?
Well, first you have the fundamental research phase, which for him was at a place like Bell Labs. Then you have the academic phase, where you institutionalize that knowledge, which he did at NYU.
And then the final stage.
The final stage is scaling it up in a hyper-competitive, massive-scale environment, which is exactly what he did at Meta. So, to understand his journey is to understand the last 30 years of technology itself.
All right, let's start at the very beginning. His early academic life. He was born July 8, 1960, in a suburb of Paris.
In Soissy-sur-Montmorency, to be exact.
And his education was very technical, very rigorous from the start. He got his Diplôme d'ingénieur, an engineering degree from EASY Paris in 1983. And then he went straight into the deep theory, getting his PhD in computer science in 1987 from what's now part of Sorbonne University.
And that PhD thesis from 87, it's a really important historical document. It's called Modèle Connexionniste de l'apprentissage, which is just connectionist learning models.
So even then, he was focused on how these networks learned.
Right from the jump. And in that thesis, he actually proposed an early version of the backpropagation algorithm.
Which is, for anyone listening who isn't a computer scientist, that's the absolute core mechanism for teaching a neural network, right?
It is the core mechanism. The problem back then was all about efficiency. You have a network with all these layers of artificial neurons. You show it something, it makes a guess. And if it's wrong, you need a way to send that error signal all the way back through the network.
So every single connection can be adjusted just a tiny bit.
Exactly. And backpropagation is the elegant mathematical way to do that efficiently. Before that, the methods were just too slow, too clunky. They couldn't handle networks that were more than a couple of layers deep. LeCun was right there, working on the mathematical tools that made deep learning even possible.
So he's tackling this fundamental problem, and that work immediately connects him to the other Godfathers. Right after his PhD in 87, he does a postdoc
at the University of Toronto, and his mentor there was Geoffrey Hinton.
The man he'd later share the Turing Award with.
It's an amazing piece of foreshadowing. That year solidified their intellectual bond. You have to remember, in the late 80s, these guys were not in the mainstream of AI research.
Not at all.
Yeah.
The dominant idea was still symbolic AI, logic-based systems.
Right. This connectionist stuff, these neural networks, were seen as kind of a dead end by many. It was a small, tight-knit group of researchers who were keeping the flame alive during what we now call the AI winter, when all the funding and enthusiasm had just evaporated.
And then, after that postdoc, he makes the move that changes everything. The one that proves this isn't just theory.
Bell Labs. In 1988, he joins the Adaptive Systems Research Department at AT&T Bell Labs in New Jersey. And you really can't overstate what Bell Labs was at that time.
It was the place to be, the world's greatest innovation factor.
Without a doubt. And he spent 8 years there, from 88 to 96. And this is where it all comes together. This is where he develops his signature invention.
The Convolutional Neural Network, the CNN.
The CNN. Specifically, the architecture that became famous as Linnet. And the whole idea was described as a biologically inspired model of image recognition. He was literally looking at how the animal visual cortex works.
Okay, so let's break that down because this is the really critical part. Why did he need a whole new type of network just for images? What was wrong with the neural networks they were already studying?
That's the million-dollar question, and the answer is scale. Just pure brute force scale. Think about a simple black and white image. Maybe it's 200 pixels by 200 pixels.
That's 40,000 inputs for your network right there.
40,000. Now imagine connecting every single one of those 40,000 pixels to every neuron in the next layer. Even if that next layer only has 100 neurons, you're suddenly looking at 4 million connections, 4 million different weights that the network has to learn.
And on the computers of the late 80s, that's just impossible.
Completely impossible. The computational cost was astronomical. You didn't have the memory. And even if you did, the network would just overfit. It would basically memorize the training photos instead of learning the general concept of, say, what a cat looks like.
So the data itself was the bottleneck.
Precisely. And LeCun's genius was to say, okay, let's not do that. Let's build a smarter architecture with some built-in constraints, inspired by how vision actually works. And that's where the 3 core ideas of CNNs come from.
Which are local connectivity, shared weights, and pooling.
Exactly. Let's take them one by one. Local connectivity just means that a neuron in one layer doesn't connect to the entire image. It only connects to a small local patch of pixels right in its neighborhood.
So it's not trying to see the whole picture at once. It's just looking for a tiny feature, like an edge or a corner.
Just a little clue. And then comes the real magic trick, shared weights. This means you use the exact same little feature detector, the same set of weights, which we call a filter, and you slide it across the entire image.
Ah, I see. So if you have a filter that's good at finding a vertical line, you use that same filter to look for vertical lines in the top left, the bottom right, everywhere.
That's the key insight. And what that does is, first, it dramatically reduces the number of parameters the network has to learn. Instead of millions of weights, you might only be learning a few dozen filters.
And second, it gives the network a built-in superpower.
Translational invariance, the ability to recognize an object no matter where it appears in the frame. A cat is a cat, whether it's on the left or the right.
And the last piece, pooling.
Pooling, or subsampling, is basically a way to shrink the data down. After you found all these little features, you summarize the information in a region, keeping the most important signal and throwing away some of the noise. It makes the network more robust to tiny shifts and distortions.
So it's this brilliant hierarchical system. Find small local features, then summarize them, then use those summaries to find bigger features, and so on.
That was the architectural breakthrough that made processing high-resolution images feasible for the very first time.
And his work at Bell Labs went beyond just the architecture of Linnet. The sources also mention things like optimal brain damage regularization.
Right, which is a very dramatic name.
It does. It sounds a little scary. What was that trying to solve?
It was another piece of the puzzle. Remember, they were working with small data sets and weak computers. Overfitting was still a huge problem. Optimal brain damage, or OBD, was a very clever way to make the network simpler and more general.
How did it work?
After you train the network, OBD would analyze all the connections and figure out which ones were least important for solving the problem. And then it would prune them. It would cut them out.
Literally damaging the brain of the network.
Exactly. It was a way to keep the essential knowledge while getting rid of the unnecessary complexity. It made the models much more efficient and much better at generalizing to new data they hadn't seen before.
A vital tool for that low-resource environment. And then there's something called graph transformer networks.
Yeah, the GTNs. That was more focused on processing sequences of data, not just static images. Think about trying to read cursive handwriting, where one letter flows into the next. It's not a single image, it's a stream. GTNs were a way to apply these connectionist ideas to that kind of structured sequential data.
Which all shows he was thinking about the whole ecosystem of problems, not just one thing. But here's where, for me, the story gets really incredible. This isn't just a theory that sat in a lab. Bell Labs immediately gave him a way to apply this on a massive industrial scale.
This is the killer app, the proof that this wasn't just an academic curiosity.
The application was handwriting recognition, specifically for reading the numbers on bank checks.
And this wasn't some small pilot program. LeCun and his team built a system that was widely deployed by NCR and other big companies that made banking hardware.
It's hard to imagine the scale of that now. Every day, millions and millions of paper checks were moving through the financial system.
It was a huge, messy, complex problem. You have all these different handwriting styles, different pens, smudges, and the system had to be incredibly accurate. You can't make mistakes when you're reading the dollar amount on a check.
And the sources claim that this system, built on Lynette, was reading, what was it, over 10% of all checks in the United States in the late 90s and early 2000s.
10%. Just stop and think about that number. That's not a research project. That is a core piece of the national financial infrastructure. Billions of transactions processed by a deep learning network that the public had never even heard of.
It's the ultimate proof of concept. It proved, decades before the current AI boom, that neural networks were accurate, reliable, and scalable enough for mission-critical industrial work.
It answered the big question. Can you trust these things? And the banking industry implicitly said absolutely yes.
Which brings up a really fascinating question. If CNNs were so successful that they were reading 10% of U.S. checks in the 90s, why did the AI winter continue? Why did it take another 15 years for the rest of the world to catch on to deep learning?
That's the million-dollar question, and it's so important for understanding the history. LeCun had provided the blueprint, he had the algorithm, but two other essential ingredients were missing at scale.
Hardware and data.
Hardware and data. Training Lynette to read digits was possible on 90s computers, but trying to use those same ideas on much bigger full-color images from the internet, or training networks that were 10 times deeper, it was just computationally out of reach.
So we needed two things to happen.
We needed massive labeled data sets, which we eventually got with things like ImageNet, and we needed cheap, massively parallel computers, which we got, ironically, from the video game industry.
GPUs. Graphics processing units.
Exactly. The algorithm was ready and waiting in 1995. The rest of the ecosystem just took another decade and a half to catch up to LeCun's vision.
That makes perfect sense. The blueprint for the car existed, but the factory and the highways hadn't been built yet.
Yeah.
So after that huge success in 1996, he makes a move within AT&T. He goes to AT&T Labs Research and becomes head of the image processing research department.
And here, his focus shifts a little bit, but he's still working on these huge infrastructural problems. He and his collaborators, Lambo II and Patrick Hafner, developed this technology called DjVu.
Which is an image compression technology.
And a very, very smart one. It was designed specifically for scanned documents, especially ones from libraries and archives that have a mix of text, drawings, and photos.
What was the big idea behind it? How is it better than, say, a JPEG?
The genius of DjVu was that it separated the image into layers. It would analyze the page and create a background layer for the paper texture, a high-resolution foreground layer for the crisp text and lines, and another layer for any photos.
And then compress each layer separately using the best method for that type of content.
Exactly. So you could aggressively compress the background and the photos, but you could keep the text perfectly sharp and readable, which is crucial for archives. It was so effective that the Internet Archive and other big digitization projects used it for millions of documents.
So again, it's him tackling these fundamental problems of how we manage and access vast amounts of information at scale. First recognition with CNNs, now dissemination with DjVu.
It's a consistent theme throughout his entire career. He's always thinking about the infrastructure.
So after this incredibly productive period in corporate research, first at Bell Labs, then a short time at NEC Research Institute, LeCun makes a really big shift in 2003. He goes back to academia.
He joins New York University, NYU, where he still is today. He's the Jacob T. Schwartz Chaired Professor of Computer Science and Neuroscience.
And this feels like a very deliberate move. After proving the industrial viability of his ideas, he seems to be stepping back to focus on the next wave of fundamental research.
Absolutely. It was a chance to dig deeper into the theory, to explore ideas that weren't quite ready for commercial application, and really importantly, to start building the institutions that would train the next generation of AI researchers.
And the sources highlight a few key areas of his research at NYU.
Hmm.
One of them is something called energy-based models. That sounds very abstract.
It is, but it's a hugely important idea if you want to get to human-like intelligence. You see, most of the AI we use today, including the early CNNs, relies on supervised learning. You need massive data sets with labels. You need 1 million pictures of cats, each one labeled cat.
Which is not how humans learn.
Not at all. We learn mostly by just observing the world. Unsupervised learning. Energy-based models, or EBMs, are a framework for getting machines to do that.
How do they work? Conceptually.
The basic idea is that the model assigns a score, which it calls energy, to any piece of data. A plausible, correct piece of data, like an image of a real cat, gets a low energy score. An impossible piece of data, like a garbled, nonsensical image, gets a very high energy score.
Okay, so learning becomes about trying to find the low energy configurations.
Exactly. It's like a landscape with hills and valleys. The model learns to shape that landscape so that all the real-world data points settle into the deep valleys. It's a way for the machine to learn the underlying structure of reality, to figure out what's possible and what's not, without needing a label for everything.
That feels like a necessary step toward common sense.
It is. It's the conceptual groundwork for the world models he's focused on today. It's about moving beyond just recognizing patterns and starting to build an actual understanding of how the world works.
And alongside that theoretical work, he's also applying these ideas to the physical world, specifically to mobile robotics. The forces mention work on autonomous off-road driving.
Yeah, and that's a great example. Driving on a perfectly marked highway is one thing. Driving through a forest or across a field where there are no lanes and the terrain is unpredictable, that's a much harder problem.
It requires a much deeper level of visual understanding.
It requires robustness. It shows he was always committed to taking these ideas out of the clean digital world and testing them in the messy, complicated physical world.
And at the same time he's doing all this research, he's also becoming a major institution builder at NYU. In 2012, he becomes the founding director of the NYU Center for Data Science.
A huge move. That helped formalize data science as its own serious academic discipline. It gave it a home. Before that, it was kind of scattered between computer science, statistics, and other departments. He helped put it at the center of the university.
And that drive to build and shape the field went way beyond just NYU. In 2013, he and Yoshua Bengio co-found a new conference,
The International Conference on Learning Representations, or ICLR.
which is now one of the top 3 most important AI conferences in the world.
Easily. It's an absolute must-attend for anyone in the field. And it was born out of necessity. The field of deep learning was just exploding so fast that the older, broader machine learning conferences couldn't keep up. They needed their own dedicated venue.
But ICLR was different. It wasn't just another conference. It had this radical new structure that LeCun had been pushing for, an open review process.
Yes, and this is so key to his philosophy. The traditional peer review process for scientific papers is slow and secretive. You submit a paper, it disappears for months, and you get anonymous reviews back.
And LeCun argued that was holding the field back.
He argued it was an obstacle to progress. With the ICLR model, papers are published online first on a site like ArcViv, and then the reviews and discussions happen out in the public. It's faster, it's more transparent, and it allows the entire community to participate in vetting new ideas.
He was trying to build a scientific communication system that moved at the speed of the technology itself.
Exactly. It's all about openness and acceleration. It's a theme you see again and again in his career. He also ran this legendary annual workshop in Snowbird, Utah for decades, just constantly building that community.
Which all leads to this massive turning point for him and for the whole field. December 9th, 2013.
A date that should be in the history books of AI. That's the day Yann LeCun became the first director of Meta AI Research, or FAIR. He joined what was then Facebook as their chief AI scientist.
This was a seismic event. This was one of the godfathers of the field who had just built a major academic center, making a definitive move to big industry.
And it signaled that the era of deep learning as a purely academic pursuit was over. This was the moment it moved into the hyperscale engine room of one of the biggest tech companies on the planet.
So what was the crucial difference? What could he do at Meta that he just couldn't do at NYU, even with all his resources there?
3 things that no university can ever provide at that level: scale, hardware, and the feedback loop.
Let's break those down.
At Fifth Fire, he suddenly had access to data from billions of users flowing in real time. That's a scale of data that's just unimaginable in academia. Second, he had access to giant, custom-built data centers full of GPUs designed for one purpose: training massive AI models.
And third, the feedback loop.
The ability to actually deploy a new model to millions of users overnight and see instantly how it performs in the real world. That cycle of idea, experiment, deployment, and feedback could happen in weeks at Meta, whereas in academia, it might take years.
So all of his foundational ideas, the CNNs, the energy-based models, they now have the perfect greenhouse to grow at an exponential rate.
And they did. Everything from the news feed to ad targeting to content moderation to the language and vision models Meta uses today. It was all built on the foundation that LeCun and the FAIR team established. It was the decade where deep learning became completely, undeniably industrialized.
Which, of course, led to this incredible cascade of global recognition for him and his collaborators. We have to talk about the 2018 Turing Award.
You do. I mean, the Turing is the Nobel Prize of computing. Getting that award It was the ultimate validation. It was the computing establishment officially declaring that the connectionists had won.
He shared it, of course, with Bengio and Hinton. And the award citation specifically mentioned their conceptual and engineering breakthroughs.
I love that they included engineering. It wasn't just for the ideas, it was for making the ideas work. Hinton for the core learning mechanisms, Bengio for sequences and generation, and LeCun for the CNN architecture that finally unlocked visual data. It was the perfect combination.
And it really was a celebration of their persistence, wasn't it? Sticking with these ideas through the AI winter when almost everyone else had given up.
It was a total vindication. The Turing Award was the moment that deep learning officially moved from the fringe of computer science to its absolute center.
And the awards just kept coming. And what's interesting is how they connect his work to the broader tech ecosystem. Take the 2022 Princess of Asturias Award.
He shared that one with Bengio and Hinton again, but also with Demis Hassabis from DeepMind.
Which is a very significant pairing. It explicitly links the foundational academic work of the Godfathers to the leader of one of the most successful industrial AI labs today. It draws a straight line from the theory to the application.
And then the 2024 Vin Future Prize paints an even clearer picture.
Because that one was shared with an even bigger group. The three Godfathers, plus Fei-Fei Lai, and Jensen Huang, the CEO of NVIDIA.
And that's the whole story right there. That award recognizes the complete system that was necessary for the deep learning revolution. You have the algorithms from LeCun, Hinton, and Bengio. You have the massive dataset ImageNet from Fei-Fei Lai's team. And you have the hardware, the GPUs, from Jensen Huang's NVIDIA.
Algorithm, data, and hardware. The holy trinity of modern AI.
You can't have the revolution with just one or two of those. You need all three. And that prize was the ultimate recognition of that entire collaborative ecosystem.
The recognition also came from the highest levels of government and engineering. The Queen Elizabeth Prize for Engineering in 2025.
Again, framing his work not just as science, but as a world-changing piece of engineering.
And in 2023, he was named a Chevalier of the French Legion of Honor.
Which is the highest order of merit in France. It's his home country recognizing that one of their own has fundamentally reshaped the global technological landscape. It's a beautiful moment that brings his French-American identity full circle.
It all just paints this picture of a career that has had this profound, sustained, and universally recognized impact on the world.
So after all that, after inventing the CNN, industrializing it at Bell Labs, building an academic powerhouse at NYU, guiding Meta's AI strategy for a decade, and winning every major award you can possibly win, what's left to do?
That is the question. And according to our sources, we have an answer. The news from November 2025 is that Yann LeCun is leaving Meta.
After 10 years as chief AI scientist, he's leaving to launch his own startup. And this isn't just him retiring or moving to a new company. This is a statement. He's pivoting to what he sees as the next great unsolved problem in AI.
So what does this all mean? The focus of this new venture is very specific, and I think the wording is important. It's world model architectures and human-like artificial intelligence.
That phrase, world models, is key. It signals a complete shift from the kind of AI that dominates today.
How so?
Think about what current AI, even the most advanced large language models, really does. At its core, it's a hyper-sophisticated pattern-matching machine. It's incredibly good at recognizing what's in a picture or predicting the most statistically likely next word in a sentence.
But it doesn't really understand what it's saying or seeing.
Exactly. It lacks a model of how the world actually works. It doesn't grasp cause and effect or what you might call intuitive physics. It has no common sense.
So give me an example. If you show a current AI a video of a glass tipping over on a table.
It could write a perfect caption, "A glass is falling off a table." But a world model would do something more. It would anticipate. It would understand gravity and momentum and fragility. It would know, without having to be told, that the glass is going to hit the floor and shatter into 1,000 pieces.
So it's about building an internal simulator of reality inside the AI.
That's the perfect way to put it. It's moving from prediction of words to prediction of the future state of the world. It's what would allow an AI to plan, to reason about the consequences of actions, to handle situations it has never seen before. It's the leap from recognition to cognition.
From System 1, that fast, intuitive pattern matching.
To System 2, the slower, more deliberate, reasoning part of intelligence. That's the mountain he's setting out to climb now.
And you can see his commitment to this direction in his other ongoing work. He's still a co-director of the Learning in Machines and Brain program at CFAR.
Which is all about that intersection between neuroscience and AI, trying to learn from the ultimate world model, the human brain.
And maybe most importantly, given his history, he's a scientific advisor to this French research group called QTI.
Yes, and QTI is a very interesting organization. It's backed by some huge names in European tech and finance.
Lev Rodolphe Sade, even Eric Schmidt.
Right. And their entire mission, their founding principle, is that all of their research, all of their models will be completely open source.
That feels like a direct challenge to the current trend in AI, where the most powerful models are kept proprietary and locked away inside a few giant tech companies.
It's the ultimate expression of the philosophy he started with ICLR. He believes that this next generation of foundational AI is too important to be controlled by any one entity. His involvement with QTI shows a deep commitment to making sure that the tools to build a human-like intelligence are available to everyone.
So he's not just trying to invent the future of AI, he's trying to shape the culture of how it's built and shared.
Absolutely. He's pushing the scientific frontier and the philosophical one at the same time.
Okay, so to wrap this all up, to summarize this incredible journey, Yann LeCun's career is really the story of modern AI in miniature.
It is. He starts in the mid-'80s working on the core math of backpropagation. Then at Bell Labs, he has his watershed moment, creating the convolutional neural network.
And he doesn't just create it. He proves its value in the real world with that system that read more than 10% of all checks in the US. The first huge industrial success for deep learning.
Then he moves to NYU, where he solidifies the academic field, helps create the Center for Data Science, and changes how research is shared with ICLR.
And then the decade at Meta, taking all those ideas to planetary scale, and in the process, collecting every major award in science and engineering, from the Turing to the Vin Future Prize, which recognized that whole ecosystem of hardware, software, and data that he helped create.
His career is the thread that connects those abstract connectionist ideas from the 80s to the powerful industrialized AI that shapes our world today. And now, the man who built so much of the present is leaving it all behind to focus purely on the future.
The person who taught machines how to recognize things is now setting out to teach them how to understand things.
That's it, exactly. And that brings us to the final thought we want to leave you with. LeCun's early career was all about solving the problem of perception, of recognition. That the generation of AI he built, the CNNs, mastered the question of what? What is in this image?
And now he's focused entirely on world models.
Right. So the question for the future is this. If that last generation of deep learning was about mastering the what, how profoundly will this next generation, the one focused on world models, master the why and the what if? If CNNs gave machines eyes, will world models give them imagination? That's the challenge that will define the next decade of AI, and Yann LeCun has put himself right at the heart of it all over again.